So if you plot the axial load, this is present load over undeformed area. So this is proportional to the axial load, because undeformed area does not change. Undeformed area does not change. This is not true stress. This is nominal stress or engineering stress. So the response you get is not symmetrical in tension and compression. So you can say this is a weakness of this material model. Unless you have a material that has different response in tension and compression, this is not a good representation of that material. Now, of course, you can say, if this is not good, what should I do? What should I use? There are many possibilities. So, I can use, if I like, say, sigma ij equal to minus some constant times delta ij plus, let me not write minus sign, f1, f2, bij, I will explain what these are, plus f minus 1, b inverse ij. So b here this f was the deformation gradient we wrote, which I have raised now, but f was the deformation gradient. So this b is derived from the deformation gradient. This is also quadratic in the displacement gradients, like E is quadratic in the displacement gradients. So this B is also quadratic in the displacement gradients. But this is Cauchy stress, not the second Piola-Grikov stress. Cauchy stress cannot be written something like this. Cauchy stress cannot be derived, or there is no strain energy density that serves as a potential for the Cauchy stress. Okay, but this is a good constitutive relation. I mean, it is fine. And if you want to say use something similar to what we did before, you can say I will use, instead of this one, I will use sigma ij equal to lambda bkk delta ij plus twice mu bij. This one is not equal to, this does not give you zero stress in the undeformed state. So if you want zero stress in the undeformed state, we have to subtract lambda plus 2 mu delta ij. Then you get zero stress in the undeformed state. Because in the undeformed state, B is identity. So this term will cancel with that one. bkk is 3. So that one will cancel with this. But the one we wrote for, like this one also does not give you zero stress in the undeformed state unless f1 plus f2 plus f minus 1 is 0. So in nonlinear theories, there are many choices. We don't know which one is the appropriate. To find out which one is appropriate, you need experimental data. We cannot sit in vacuum and say this constitutive equation will work. No constitutive equation works for every material. We are lucky that Hooke's law gives us good results for every material. But that is in the small deformation approximation. But for large deformation, there is no such thing as having one constitutive relation that will work always for every material. And I cannot answer For my skin, which constitutive relation will be good? For my liver, which constitutive relation will be good? For my heart tissue, which one will be good? I cannot answer that question. कोई नाम नहीं है. नहीं, इनके नाम नहीं है. अगर होता मैं बता देता. At least I don't know it. हाँ जी? अभी लिखा तो था. I think I defined BIJ. Maybe I forgot. I did not define it. हाँ? अभी तो लिखा था F, यहाँ पे लिखा हुआ था F क्या है? वो इस डेल्टा IJ प्लस, हाँ? वो तो पुरानी बात है. ये तो पुराना लिखा हुआ है. उस समय तो ये लिखा भी नहीं था. अभी F की डेफिनेशन लिखी थी. प्रणव ने पूछा था, कहते वो what is F called as a deformation gradient? F1 F2 are constants. नोटेशन है यार, क्या है तुम इसको 1 कह दिया तो इसको -1 कह दिया, बिकॉज दिस इज -1 देयर, इट्स ए कांस्टेंट. तो in the most general case they are actually functions of invariants, but that will take us into a different direction. B अभी बताया तो है वो inverse of B. It's inverse of matrix, right? Yeah, so that's inverse of a matrix. Okay, sorry. They don't, yeah. F3. Constants, F1, F2. In the most general case, they are not constants, but that one, then you will keep asking me, how do they depend upon these invariants? And I don't know the answer. I cannot give you the values of F1, F2, F3 either. You will say, what are their interpretations? I have to derive those. So it's a long story. I mean, if we can talk about this the whole day, but that is not what we want to do, though. The main thing you need to know is the weakness of the material we are going to study, because that material has this property. The response in tension and compression is different. Modulus at zero, like this is continuous slope here. But beyond that, if you go to, say, 50% compression or 50% tension, the loads are totally different. This is a property of that material. It does not, all it tells us is that material, I wrote Saint Bernard Kirchhoff material, which is very commonly studied because it's easy to study, is not necessarily a good model of a physical material. Okay? So it has weaknesses. The only thing it will illustrate is how do we solve a nonlinear problem. It does not mean that if you take a bar made of rubber, any rubber you like, that constitutive relation will be a good model for that rubber. There is no implication of that type. So only to illustrate to you how to do a nonlinear problem, nonlinear elastic problem. So there is no implication that that I can go to my surgeon and tell him, use this constitutive relation and then find the force required to operate on me. I may not come out of the surgical room. So there is no such implication. Okay? Because to do that, we really need to take the tissue, test it, then see if the stress strain curve, not only for tension, but for torsion and compression and shear, etc., matches with the predictions from that constitutive equation. And then, yes, there's some hope I will come out alive. But otherwise, no. Fortunately, things work. I mean, don't my word so seriously, because every day there are like hundreds and hundreds of operations done. And now they are being done by robots, which are basically pre-programmed. They are not pre-programmed for my tissue, but they somehow work fine. So things are okay. I mean, again, these are designed by us, engineers. Key thing is factor of safety. And that's what saves us. Okay. Anything else you want to ask before I erase up some of this stuff? Okay, now I cannot erase this because I need this one. So who will tell me is Euler-Bernoulli beam theory a good approximation for this kind of problem? No. So he was quick in saying no. Why? So क्या Euler-Bernoulli beam theory क्या किया large deformation? We cannot use it for large deformations. That's a kinematic assumption in the theory. Pardon me? Sorry, I'm slowly. That plane sections remain plane. So is that not going to be the case? So in the Euler-Bernoulli beam theory we wrote yesterday, we said W equal to W0 of x, and U is minus Z delta W0 over delta x, where Z is really measured from the neutral axis. So the reason this will not work, pardon me? Yeah, sorry, go ahead. Excuse me, it does not account for the change in thickness. You are right. Number two, how will I say the load is acting on the top surface? Because in that theory, the vertical displacement does not depend upon the z coordinate. So as far as if I make these assumptions, then it does not matter whether I apply the load on the top surface or middle surface or bottom surface. I will get the same answer. So we need, if we want to distinguish where the load is applied, then we need to modify these assumptions. So that's what we are going to do. So we are going to not use these assumptions. So we are going to say U as a function of x and z or z is U0 of x plus z phi of x. I do not know phi. I do not know U0. And same thing for about W. So I'm W x z is W0 of x plus z psi of x. It's not a very refined theory. So don't expect excellent results from it. If you really want to do the problem seriously, then we should do two-dimensional finite element. And that should give you, but I have not covered that. I have not covered two-dimensional finite elements. So we only have talked about one-dimensional problems. So that's why I'm not going to go into that one. That will take us some more time. Okay, so this one, if you keep on refining the mesh, which means keep on taking more and more elements in both x and z direction, you will get a very good answer. Very good means as good as you wish, because if you keep on refining the mesh, it will converge, and then you are done. But in this case, you will get an approximate solution. And that's what the beam theories and plate theories are designed for, to get you an approximate solution. This is also approximate, but this is a better approximation than that. Okay, does it make sense? You don't like it? Bolo. No, यहाँ कोई beam theory नहीं use कर रहा है. When you are two-dimensional elements, like you have either rectangles or square elements, there is no assumption of any beam theory. No. Here there is an assumption of a beam theory. Because here it says u varies in the z direction, it's a linear it's an affine function or a polynomial of degree 1 in z. That's an assumption. If you do the problem with the finite element method, or if you are lucky, actually some problems we can do analytically, but I'm not going to do those. If some problems we can, if you do analytically, don't get that kind of variation in the displacements, which is a polynomial of degree 1 in z. So that's a very crude approximation. As Euler beam theory is a very crude approximation. So it's an approximation, not necessarily a good one. But if you want to improve upon it, you can say I will take z square times another function, 2 of x. If you don't like that, you can improve. Say I will take another term here. So basically you are expanding in terms of Taylor series and keep on adding more and more terms. But as you add more terms, you have more unknowns. Now you have 1, 2, 3, and 4 functions. Then you will do the same thing here. You will have 8 functions. So most likely your solution will be better than what it was with 2 terms in each case. So it depends upon how much work we want to do. So in reality, if you really want to be strict, we should keep on expanding in terms of z, the z coordinate, and keep on solving the problem with different orders here till the solution has converged. But our goal is only to learn how to do it, not necessarily find the most accurate solution or converged solution today. Does it make sense? Because we are trying to learn how to do a nonlinear problem. So let's just forget it. So if this one is a little bit, just tiny bit better than Mindlin's plate theory, not a whole lot better, but tiny bit better. Tiny bit better means because we have this term. And Mindlin's theory, you don't have this term. So that's all, I think. So we can call this first order, shear, normal, deformation. Actually, we don't use the word deformation. FS. Well, if you want to use DT, then I can call it FS and DT. So it's first order, shear, and normal deformation theory. Normal because you have a normal strain now, even though it's a constant. If you take delta W over delta Z in the linear approximation, it's a constant as a function of Z. You're not happy. Sure? Because you are said you will write a code tonight. Oh, not for this. Okay. Oh, okay. So I cannot give him homework now because he has graduated, right? So if you take this, now what we do from this is then you find E11, E33, and E13. Also, to make life a little bit simpler, instead of solving for U0 and phi, and eventually we will get nonlinear equations for these four functions. But we are going to simplify further today, just to get a first approximate solution. So what we are going to do is, we are going to say U0 is A1 plus A2x plus A3x squared plus A4x cubed. Because yesterday our polynomials we had, they were cubic in x. So that's why you just stopped at cubic in x. So we have four unknowns. In U0, so we're going to write the same thing for W. So same thing for phi, same thing for W, and so W0 and psi. So like here we have B, here we can write B1, here we can write C1, and here we can write C2. Is it okay? So we have no, this is an approximate solution. We are trying to find now, if we know these 16 constants, A1, A2, A3, A4, B1, B2, B3, B4, and so on, then, excuse me, if we will get our solution will be in terms of these 16 constants. Another possibility is, which will be a better approximation, I think, if you do the problem for the linear case, small deformation theory. If you do the problem for a small deformation theory, you can find mode shapes. Which means I'm really doing vibration problems. So I'm doing vibration problems. So you find first frequency, first mode shape, second frequency, second mode shape, third frequency, third mode shape. So if I can write my mode shapes as psi1, which is a function of x, psi2 as a function of x, and psi3 as a function of x. If you notice, I always put 3 dots. I don't know if I did not point that out, but I am always putting 3 dots. It's a mathematical requirement. If you put 4 dots, it has no meaning. If you put 2 dots, it has no meaning. 1 dot, of course, is a period. So if you put 3 dots, that means you have this continuation. Terms are continued. So that's why we put only 3 dots. Not 1, not 2, not 4, not 5, only 3. It's a universally accepted convention among mathematicians. Okay, so if in this case now, if you do that, and you can, in some cases, you can also find the mode shape for the in-plane vibrations. Even though most people don't consider that, but you can find mode shapes for the in-plane vibrations. Then you can express U0 as in terms of mode shapes of the in-plane vibrations. So we can express W0 as some other constant times psi1. And probably 2 mode shapes will be enough. So you can reduce the number of unknowns by considering only 2 mode shapes. This is for W0, and then I don't know what to assume for psi and phi, and U0. But this will give you a reasonably good solution, but you have already done half of the work, because in finding the mode shapes, you did some work. They are not free. I mean, they are given in many books, actually. I should not say they don't require a whole lot of work. For Minden plate theory, as well as Euler Bernoulli beam theory, these mode shapes are given in many books. So you can they are given in closed form. If they are not given in closed form, you can digitize the data and fit a smooth curve by the least square method so to get these functions, which is the same thing. Not necessarily for the liver case, but okay. So if they are hyperbolic, deflected shape, you have to find the deflected shape first. Again, it's in the books. And yeah. So if you go back to the same thing. So it's it's your choice. Remember, the choice of the basis functions will determine the quality of your approximate solution. So if your choice of basis function is very good, you can survive with one or two unknowns. But if it is poor, then you have to take more. So let's stick with this because I don't need to find the mode shapes and I don't need to find the frequencies. Are we together now? So we are going to assume that our approximate solution has these 16 unknowns. A1, A2, A3, A4, B1, B2, B3, B4, C1, C2, C3, C4, and D1, D2, D3, D4. And these are all polynomials of degree 3 in X. That's because of my ignorance. I don't know anything better. I do not know whether indeed I should take cubic polynomials for each or not. So since I don't know it, I'm just assuming they are, all of them are equal. They are treated equally. After you have solved the problem, of course, you will say, hey, why did not you do it? Why did not you take a simpler one? But I don't know the answer. So now I find E, 1, 1. All I have to do is differentiate these to find E1. So U, we assume U is U0 plus Z times phi. So you substitute these in here. You will need to write a software, like you will need to write MATLAB, either Mathematica or MATLAB, but this is doable. So you substitute for U0 here and U and phi here, same thing, W0 and psi. So these are cubic polynomials in X, and they are polynomials of degree 1 in Z. Find E11, E33, and twice E13. Obviously, I cannot do it in the class now. But in principle, you can do it. So you start with this definition. You find the first derivatives, right? That actually one can do by hand, but every Mathematica, MATLAB, Maple will do it. Symbolic manipulation. Substitute in these expressions, you will get expressions for strains in terms of A and X, and there will be A square terms also now. So there will be terms like A1 square, A2 square, A1, A2, and so on. Does it make sense? So once we have that, we can find W, that W we are talking about there, and for the expression I wrote, I think W is summed on L and summed on M. So the expression I wrote for S corresponds to this expression for W. I think my memory is correct. Or if you differentiate this, you should get the expression I wrote for the second Piola-Grikov stress tensor. Now you know where we are headed. So now you find the potential energy. So if we integrate this with respect to dx and dz, So it's 0 to L, 0 to H, and minus F times the W, not delta W, because I'm not taking the variation, I'm finding the potential energy. And this is W now is a function of X and at the upper surface. And then you integrate this with respect to. So we are assuming that our load is dead, it always stays vertical, and the load given to us is force per unit undeformed length. Dimension perpendicular to the screen is 1. So what will this come out to be? After you have integrated with respect to X and Z. So what will be our answer in terms of those 16 constants? So what, after we are done, we will get this pi as a function of A1, A2, B1, B2, C1, C2, D1, D2, etc. The last, so up to like D4. And it will be a nonlinear function. It will be nonlinear because you are going to square these plus you are going to square here again. You are going to square here again. So you will get A1 to the power 4, A to the power 4, A1 cube. I cannot tell you exactly what you will get. Does it make sense? So now from here onwards, there are two ways. Either you can borrow or download any software from internet, which is either optimization software or conjugate gradient method. It will you need to find the values of A1, A2 up to D4 so that the potential energy is minimized globally. Yeah, I'm going to come to that too, yes. So when you do the minimization by conjugate gradient method or any other method, makes no difference, you will need initial guesses. Sometimes your initial guess is bad, you go on a path that the solution does not converge. You don't get the minimum. So one way to get those initial guesses is what Professor Gupta said in the beginning, that you look at the deformed shape for the linear elastic problem. So you have the deformed shape for the linear elastic problem, which means you are using not Euler beam theory, but the stress strain law you are using is not the potential energy is not this one, but it's a quadratic small strains, not large strains. So if you take, I think you are wondering what I'm talking about, but it's I wrote Hooke's law as sigma ij equal to lambda ekk delta ij plus twice mu eij. So these e's are whatever I will put in circle here is e. So this part, the one I put in the box, corresponds to small strains, E11, E11, E33, and please speak up. You have a question, yeah. It's okay, you can ask. You were asking him, you can ask him. I'm sorry? What do you mean you are not getting anything? Before the coffee break, I wrote SLM equals lambda EKK delta LM plus twice mu ELM. I wrote Saint Venant Kirchhoff material. The stored energy function for this material is this. If you differentiate this with respect to E, you get this. Does it make sense? If you differentiate stored energy function with respect to E, you will get this, the right-hand side I wrote here. And that is the first Polar-Kirchhoff's, sorry, that is the second Polar-Kirchhoff's test tensor. You still don't like it. So you have to take my word for it then. That indeed, if you differentiate this with respect to E, you get this. See, one way to convince you is, if you differentiate with respect to E, so this term will disappear, so that you get the second term. Okay. And then the first one, the trace of E is EKK, that's E11 plus E22 plus E33. So now if you differentiate, you will get twice EKK, then you differentiate EKK with respect to ELM. So you will get delta LM. Maybe I think I missed the factor of 1/2 here. So probably I missed the factor of 1/2, but and something close to that. And if I miss 1/2, I can change the definition of lambda and mu, or their values. Intuitively, does it make sense now? Because I know if I differentiate, I will get twice of lambda. So I should have put 1/2 here of the whole thing. Then probably I will get this one. But anyways, accept the factor of 1/2 or so, it's okay. So we can find then, I was trying to talk about how to make an initial guess for A1, A2, A3, A4. And so you do the problem for a Hookean material. The stored energy density for this one is 1/2 lambda EKK square plus, I think, mu EIJ. No, I think I'm okay with the factor of 1/2. This is the same thing as we wrote here, except we are replacing big E by little e. And that is the problem most of us do in small deformation theory, that is the stored energy function. And if you do this stored energy function, you will still get, all these constants, A1 through D4, except you may not get any fourth power or third power, but you will get all of these. And if you solve the problem for the small deformation, you will get good initial guess for these 16 constants. And now with that initial guess, you solve the problem. Okay. So first, before I go further, does it make sense now or not? I mean, you still don't like it. Speak up. I'm sorry? Okay. So still it's a minimizing procedure. This is same for both small and large deformations. For large deformations, you find E from all of these terms, keeping these ones and these ones. Then you find the stored energy density. Because these are quadratic terms, so they will have A1 square in it, A2 square in it. And also, when you come here, you are going to square again. So they will have a1 to the power 4, a to the power 4. Something. Now you integrate with respect to x and z. So x and z are gone. What will appear here is the length of the bar and the height of the bar, which we don't change, right? They don't change. So your potential energy here will be in terms of these parameters, 16 parameters, but nonlinear function of these parameters. So either you can use programming, like any optimizing algorithm, or we will talk about what else we can do. Okay. So when you use any method, you will, because these are nonlinear, you need initial guesses. Like yesterday, we said initial temperature was 50, 70. 70 was not a good guess. 70, I think you did this simulation. 70 was not a great guess. 50 was a better guess. So in the nonlinear problem, the final solution and how many iterations it takes depends upon the initial guess. None of us is smart enough to figure out what should be the initial guess. And I proved that yesterday that I'm not smart enough to figure it out. Because I gave you 70 and it should have been 50. Or maybe 40 would have worked too, but 70 was not a good choice. So here now, what should be that guess? Okay. Professor Gupta has done many optimization studies for molecular mechanics simulations. And Tinker, well, he used the software Tinker. Depending upon what you take for the initial guesses, you can keep on iterating forever. So we are trying to find now the initial guesses. Okay, to find the initial guesses, you do the linear problem. So in the linear problem, these strains are now small strains, which means you have only these terms. These terms will have a1, a2 to the power 1, not 2. You come here, you square them, so you will get a1 square now. So instead of getting your potential energy as a1 to the power 4, it will be a1 to the power 2. So either you minimize the way we did it, or you do what we are going to do now. Okay? So now let's do that. We have found this W. In terms of these 16 constants. And instead of writing A1, A2, A3, let me write alpha. So we have alpha. So I have, not W, this is my potential, not sorry, W. My potential energy will come out to be a function of 16 unknowns. So I do the same thing what we did yesterday. I say this is, expand this in terms of Taylor series. Actually, so expand this in terms of Taylor series. If my initial guess is correct, this really should be 0. Because for the minimum, the first derivative should be 0. But probably it won't be 0. So what we have to do now is then we have to find when will this quantity be 0. Because I need to, this is again a solution of, this will again be 16 equations because you are differentiating A1, A2, A3, A4 up to 16. Right? If you are doing a linear problem, these 16 equations will be linear in A because pi will be quadratic in A, and if you differentiate, you will get linear in A. So linear equations are not hard to solve. So you can solve them. So you have now a solution of these linear equations which you have solved. So this is now A alpha. You evaluate it at the linear solution. Plus the second derivatives. Again, this is evaluated at linear solution. And then you have the variation. So we have to solve these equations. This should be 0. This becomes the force vector. This becomes the so-called stiffness matrix. And this is the increment. No. Oh. No, because I'm differentiating already once. Yeah. I could have given this thing a different name. So what will happen is that you need to solve K delta A equal to F every time you update K. Like we did yesterday, every time we updated our thermal conductivity. So here we are updating our stiffness matrix every time. And it will convert depending upon the initial guesses. And now I think we, courtesy of Professor Gupta, have an initial guess. Otherwise, you can find the deformed shape, take that as a basis function. And then also, we have to somehow guess initial values of A. And there is no easy way out. If you take them equal to 0, then you will need probably 1,000 iterations. It was same like yesterday. If we had taken initial temperature instead of 50, we had taken, say, 10. Then the number of iterations will have gone up. Because eventually we have to reach the values that we got. So going from 10 to 100, well, 100 was a given condition, so that was no problem. But at the intermediate points, you are like 95. Going from 10 to 95 would have taken more time. So same thing here. Like if the initial guess is poor, we will have to do more work. And initial guess, yes, A naught alpha is from the initial guess, right? Or even if you, it's basically from the initial guess. That's initial guess, that's what. In our variation here, we have already done it. We did not account for the work done by external forces. And also the W we should take, they should satisfy the essential boundary conditions. Yeah, they will need to satisfy essential boundary conditions. This variation is 0 wherever so when you solve for deltas, A's, variation should be 0 on these interface. But the A's are here constant. So really W we choose should satisfy essential boundary conditions. So the choice I gave you, you may have to modify it a little. I'm sorry? Well, that will be a constraint on those A's, right? Yes. Yes. We will need to, actually he's right, we will need to satisfy that boundary condition. So we will need to choose W's and U's such that the boundary conditions are satisfied. So that will impose a constraint on our 16. See what we wrote, if you set x equal to 0, you will get A0 equal to 0. And A1 equal to, sorry, we had A1, A2, A3, A4, you will get A1 equal to 0. Same thing, U is 0 here, you will get B1 equal to 0. and then C1 equal to 0, and D1 equal to 0. So four of those will be automatically satisfied. And then instead of 16, you will be left with 12. And if you still want to improve, you can say, I will take my solution as x square, x cube, x to the power 4. You still have 16 unknowns. But you are right. We will need to satisfy the boundary condition. The essential boundary, not natural, essential boundary condition. Natural is here. The load one is here. The work done by the loads. So, yes. I'm sorry? No, see, no. See, what we wrote was that W of x, z is A1 plus A2x plus A3 x square plus A4 x cube plus z times B1 plus B2x plus B3 x square plus B4 x cube. But at x equal to 0, W should be 0. It's a Clamp-Tat. You are right, I had forgotten that part. So at x equal to 0, W is 0. If you set x equal to 0, all these terms disappear. So which means I should take A1 and B1 equal to 0. Because it has to hold for all values of z. Right? So that gives me now only 3 constants here and 3 here. And same thing for u. When I write for u, I had a similar expression. So that will give me C1 and D1 to be zeros. So if I still want my solution to have 4 unknowns each, we can go up to the 4th power of x here. Then I will still, instead of A1, A2, A3, A4, I will put A5 also. And the more term you take, the better approximation you get, but we have to do more work. And again, please, we cannot do by hand. I mean, you can, but chances of making a mistake by hand are very high. So it's better to use a symbolic manipulator that will integrate with, that will differentiate these terms, square them, square again, integrate with respect to x and z. These are polynomials, no problem. Any symbolic software will do it. So you will get terms involving h square, h cube, and so on, plus length. Then you will get something like this. And we have to minimize this quantity. So with some luck, we can find the minimum. In a nonlinear problem, it's always luck. We found that out yesterday. It was a very simple expression for thermal conductivity, alpha plus beta times temperature. If we had assumed a little bit more involved, then the number of iterations would have gone up. Plus, we may not have been able to solve it analytically. And then we would not have been able to answer the question you raised, which one should we look at? Actually, what we can do is, to choose which branch. Numerically, we did not get 2 branches. But analytically, we need to look at the free energy, which really means I need to find an expression for the Helmholtz free energy corresponding to the, I need to find the expression for the free energy, internal energy, and the entropy. So free energy is then internal energy minus eta times temperature. That quantity should have been minimum. This one, all of these will depend upon temperature only, because we had a rigid body. So in our case, the specific heat did not play any role because we were talking about a steady state heat conduction. So this quantity did not play any role. So what we had to check is if the entropy production for our problem is non-negative. Which one of the two solutions is giving us entropy production non-negative? And if the entropy production is less than 0, we are in trouble. So that solution cannot be possible. But we did not check anything like that. But that is a check. We did not impose this condition. When I thought about it last night when after you asked me in the daytime, that what is the missing principle? If it were a mechanical problem, we would have computed the free energy. Here also we are computing free energy, but free energy is dependent only on temperature. It's not a function of anything else. It's a rigid body. For the temperature, the only thing that shows up here is entropy production should be positive, non-negative. And that we can check from the two solutions we were getting from our quadratic equation, which one of those two gives us non-negative entropy production. Only one of the two will give us. I mean, you have to take my word for it. I did not check it. So that one is the admissible one. But the other one is not admissible. Fortunately, from numerical solution, we got only one. And we did not check any of this stuff, but that is what governs. This is second law of thermodynamics. We use the first law to drive the equation. So this is the second law of thermodynamics, which we cannot violate. And that would have determined which one of the two analytical solutions is admissible. Okay, so I think the ball is in your court now, whether you want to work on it in the afternoon on this problem, because I cannot do by hand. And if you are efficient in writing the software, I think it can be done. But I'm not going to hold you responsible for it. It's up to you if you want to practice this in the afternoon or not. And if you don't want to practice it, then we don't need to come even. It's up to you, because that's the task for the afternoon is assuming the expressions for U and W and differentiating them, finding strains, finding the potential energy, and then minimizing it either by using a program from the internet, an optimizing algorithm, or we can do something like that. Since these are nonlinear equations, we will have to do iterations. Sorry, I mean, there's no easy way for me to do it. I had not done this problem before. Actually, I thought of doing this only day before yesterday. So it's not that I had done this thing like back home. Otherwise, I would have given you the solution. We have done this problem numerically a long time ago, okay, for a transient problem. Same theory, no change, except we use the finite element method. Like where I'm showing you, we divided the beam into, we have done both for a beam and a plate. When I say we, the graduate student did it. I did not do it. The student did it. So don't. No, WE. That means you and I. Like he and I. But no, it's not. But I did not do. No, WEI is a student's name. But no. Actually, no, it's not WEI who did it. It's a art gang. GENG. He did it. So the theory is exactly the same. Actually, Noha Hassan also did it. She did PhD. God knows when, maybe 15 years ago, or no, 10 years ago, 10 or 12 years ago. And Art Gang also did PhD about 10, 12 years ago. Yeah. In my group, they only work on nonlinear problems, non-linear problems. They don't get PhDs for linear problems, period. No, we do. Seriously, even though Shakti did his problem is also nonlinear. We cannot say it's linear because the MD potential he used is not quadratic in the variables. So it's not a linear problem. In my group, I think I misspoke. Senthil Whale did linear problems. He's the only one. I think he's the only one who did linear problems. But there's a but. Because at that time, I think my memory is correct. Senthil Whale did linear problems only. So one of the issues we were facing for the simply supported plate, Srinivasan Rao from IISc Bangalore, they had given an analytical solution of the problem. So this laminated plate, so it's a fiber reinforced composite plate, and for the simply supported plate, Srinivasan Rao actually is thought to be correct historically. Vlasov in Russia had given the solution by the same method probably 10-15 years before Srinivasan Rao did. I think my memory about years is correct. The names are correct. I think my memory about the years is also correct. That this is somewhere along 1970 to 71. This is probably 1957 or so. But the year may be wrong, but I think it's probably correct. Anyway, so he had given in Russia, he had given the solution of the same problem by the same method. Srinivasan Rao gave the solution. At the same time, Pagano in the USA also gave the solution by using the same method. So depending upon in which continent you live, some people call it its Pagano solution. Some people call it its Srinivasan Rao solution. Some people call it its Vlasov solution. So to Senthil, I suggested that we need to find an analytical solution for a clamped plate. Because if you look at aircraft structures, very few of them are simply supported. So I said, Senthil, let's do it by, we did not want to do finite element method. Of course, with the finite element method, we could do it. I mean, that's no big problem. It's using a software. Why should he get a PhD? An undergraduate student can run the software. It's true. I mean, if you have actually, you won't believe, couple of seniors, which means fourth-year students, they found mistakes in commercial software. Like one of them found a mistake in LS Dyna, which we paid like $50,000, $100,000. And that student, in one semester, this was his senior year project. And we were getting results which did not make sense. Then he found a mistake. But it was, storage problem. The length of the array was not right. To make the long, okay, so I think I misspoke when I said none of the persons in my group has done a linear problem. So Senthil, he did problem for nonlinear, he did problem for linear elastic materials, but the edges were clamped. And he used Eshelby's formalism. The way he told me was that he was taking Mike Hayer's class, and somewhere when he was taking notes, it struck to him that maybe we can use this approach to find an analytical solution. And he did. It worked very well. Then, of course, he extended that to many cases. Now, once he did for a clamped plate, that was the problem. Then he could do this edge is clamped, this is free, this one has different boundary condition. So each layer could have a different boundary condition, which is, I mean, if you try to do it numerically, you may not be, finite element, Abacus or LS Dyna may not like you very much. But analytically, he could do it. And that's did for a functionally graded material. Then he studied vibrations. His work is very well cited, Senthil Wales. So I think I misspoke when I said nobody does a linear problems in my group. But yes, generally speaking, it is true. Out of 34, 35th will graduate next month. Actually, out of 5 papers of his, 3 are on linear problems, 2 are on nonlinear problems. But the other 3, he did not want to do nonlinear problem. I don't know why. I have no idea why, because in the course project, he did a nonlinear problem using one common nonlinearity, but I said, no, we need to do full nonlinearity like this one. He said, the software doesn't work. It worked for Noah Hassan, it worked for Art Gang, but he says it doesn't work. So I don't know. But those guys, like both Noah and Art, they wrote their own software. They did not use Abacus or LS Dyna. It's true, in LS Dyna or Abacus both, this material model is not there. So you have to write your own UMAT or ViewMat for those softwares. The Saint Bernard Kirchhoff material is not included in Abacus. But no, we have the software. If anybody wants, we give it out free. So we don't charge anything. Okay, so what is your pleasure now? What do you want to do? You want to practice in the afternoon, or you want to sleep? Because I know if you don't come, you're not going to work on it. Okay, so good. So see you in the afternoon.